Okay, you guys, today I'm going to talk to you about bond polarity versus molecular polarity. It's just a short little lesson. I know the lab asked for the molecular polarity, but I want to clarify the difference between the two. Bond polarity we already did. And to do bond polarity, you need this sheet right here. And we're going to use this band. So in order to know bond polarity, you have to know the electronegativity difference between the atoms to see if there's a dipole or not. So basically it's just asking what kind of bond is it. If it ends up being polar or ionic, it is polar bond. If it ends up having a nonpolar covalent bond, it's obviously nonpolar bond. So I'll show you an example of that in a minute. To do molecular polarity, you need this sheet. So the molecular polarity wants you to basically see if the molecule shows polarity or not. Or is there a net direction of pull between atoms? So to do this, it's really hard to do when you don't have the 3D model, but to do it with this sheet, when we look at the SP molecule, which is obviously I'm redrawing what's on the paper right here. Because this right atom is pulling electrons towards it, and this left electron atom is pulling electrons towards it, you have a dipole to the right and a dipole to the left. Those actually cancel out to nothing. So that is actually nonpolar. So it's possible that you could have a polar bond here or ionic, and your molecule might end up being non. It all depends on the shape. So the molecular polarity is dependent on the shape. The bond polarity is dependent on the number difference. If we look at the three bonding sites here, this sp2 hybrid, trigonal planar, what you end up having, now you have to understand this isn't 3D, so it makes it hard. If you have a net pull down towards that one and a pull towards that one, that basically ends up being down. So if you have down and you have up, that's also non. Okay, let's go to the next one, which is the bent right here. Now, a lot of you guys were missing this on the homework, so I'm going to also talk about this. This has three bonding sites. You have to count this as a bonding site, even though there's nothing being bonded to it. So it has 1, 2, 3 bonding sites, so it's sp2 hybrid. A lot of you guys were counting that as 2, because you're seeing 2 lines. Stupid dog. Okay, so I always have the electronegativity pulling outward. So I'm going to draw an arrow on that one and an arrow on that one. And if you guys take a look at this, do you think there's a net direction of pull? This does, because you have a net down and no other atom pulling upward. So this one's polar because it has a net pull in one direction. So when you have lone pairs, they don't count as pull because there's nothing there pulling on it. There's just hanging out dots. All right, the 4 bonding sites. Now the tetrahedral, which is drawn kind of like this, is really hard. Most kids think that that's polar because there's a net pull down, but you have to understand 3-dimensionally, these are all pulling at the same angle. So the only thing I can say about this other than showing you with an actual 3D model is it's non. Because they're all 109.5 degree angles pulling outward equally. So there's no net pull on that one. Okay, now your trigonal pyramid, which is right here, sp3, it's going to be down, 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 with nothing pulling upward. So that one definitely has a net direction downward. That's a polar molecule. Now another thing to keep in mind is sometimes these atoms out here aren't all the same types of atoms, and that's a different story altogether. I'll have to talk about that in the future. So right now we're just going to treat these as all being the same pole, and we'll deal with that later. That is polar, trigonal, pyramid, or pyramidal. Okay, then this one is bent. This is going to be like what water looks like. And I'm pretty sure you guys can see now, if you have a down and away, you have a net down, and that's polar. So when you do the lab and you come up with the Vesper shape, you can just use my little video here to guide you on whether it's polar or not. All right, this trigonal bipyramid sure looks polar to me on here. It's just very hard to describe when it's only 2 dimensions. So the trigonal bipyramid, I want you to think about this Y first, which cancels to nothing. And then you got a right and a left, which cancel to nothing. So that's a 0. And these 3 added together is 0. This whole molecule is non. Really hard problem to do, but that's how you want to think about it. These 2 cancel to nothing. These 3 cancel to nothing. Think about tug of war pulling 3 different directions. Nobody's going anywhere. Okay, the irregular or seesaw, this is sometimes called, regular tetrahedral. What you have on that one is those 2 plus those 2. So you know these 2 cancel. What do these 2 do? They're pulling down. So this thing's polar. The T, that one's an easy one to see. If you got right, then left, those cancel to nothing. And then the down obviously gives you an overall down pull. That's polar. So if you have an overall direction, doesn't matter what direction, it's automatically polar. Now here's another thing. If your bond polarity comes out non, you can't have a polar molecule, period. So if this comes out non, when you do this math, comes out between 0.2 and 0, you don't even have to worry about the molecular, it's automatically non. But it's possible that you can have a polar here in a non-polar shape. So if it's polar here, you have to automatically check the shape. I'll show you in a minute examples. I gotta move. Okay, and we're not gonna waste the time on the linear because we all know, I'm pretty sure by now, that linear is a non. All right, this 6, sp3d2, octahedral, everything cancels on that one. So you have up, down, those cancel. You got that angle with that angle, that cancels. And you got that angle with that angle, and that cancels. So that's non. Everything cancels out. Now the square pyramid or square pyramidal, you got that one canceling that one canceling that one, and then you have a net up. So that one's polar. Square is non, T is polar, and linear is non. Left, right pull cancels. These 2 cancel, those 2 cancel, that's nothing. And those 2 cancel with a net up to the right, and that's polar. So the T's polar, the linear is non, and the square planar is non. Now I'm going to show you a couple examples, and then I'm going to get out of here. So I'm going to go back to this sheet, which we did, I don't know, maybe a couple weeks ago. I'm just going to pick a couple. SiH4. So first thing we're going to do is we're going to look at the electronegativity difference on these. So H is 2.1, S is 2.5. Subtract them, we get 0.4, and that puts you right in here in the polar covalent. So it's a polar bond. Let's check its molecular shape. So if we would draw this thing out, actually, we want to draw it correctly now. So we want to go over to here. Where's that at? It's going to end up being this shape right here, tetrahedral. So we would want to go like this with that H up here. And remember, this one's a hard one because they're all 109.5 degrees. Very hard to do on a piece of paper. It's non for its molecular polarity. So polar with the bonds, non with the molecule on that one. All right, maybe two more and I'll be done. My cameraman's getting tired. Let's do XEF2. Okay, we're going to tally up the total dots. We got 8 plus 14 for a total of 22. Let's check the numbers. I'm sorry, I didn't mean to do that there. We'll save that for over here. So XE's pull is a 0. F2, F's pull is 4 for a huge difference of 4.0. That is extremely polar. It's ionic, which is as polar as you get. That becomes polar because it falls under the ionic. All right, the shape of this, just to move along, is going to look like this. It's going to be, what did we say, 14 and 8, 22 dots. So it's going to be F, F, it's going to actually look like that. Which if we look over to here, we got to go back to this sheet and see what shape it ends up being. It is going to look like that sp3d, which is linear, that's non. It's very important you draw this right. Once you draw it right, it doesn't even matter if you draw it exactly like the sheet. If you draw it right and you figure out the number of lines and the number of lone pairs, you can match it up to this picture here. And that'll tell you whether it's non or not. Okay, one more. Let's do BF3. So this one, we're going to look at the, I keep losing my paper. Here it is. So B is 2.0, F is a 4.0, difference of 2. That puts you up here in the ionic. That's definitely polar. The shape, it's going to look like this. That was actually the one we did on our homework, real similar. Ends up being trigonal planar. And if you're pulling outward, and up, these two cancel because they really end up being that with that, and it's non. Okay, well, I hope this helped you guys.